All right, so welcome back. More polar things. So example 6 here, we have a Cartesian, meaning an XY equation, that we want to write in polar form instead. So this one is x squared plus y squared equals 9. So whenever I'm having to do these conversions, I like to have all of my in-between, go-between equations. So I copied and pasted them here. So my first one, x squared plus y squared equals r squared. Well, there's literally x squared plus y squared there. That is r squared, so let's change it out. So literally in place of x squared plus y squared, the thing here, I wrote the thing there. So we have r squared equals 9. Now, similar to like when we were always getting y by itself to write functions, same idea here. We prefer to have r by itself. So instead of r squared equals 9, I can apply a square root to both sides, and I actually get two equations technically. There's r equals 3 and r equals -3. So these produce the same graph, which is a circle of radius 3. Um, just with the way the polar coordinates worked, if I do a circle of radius -3, I get the same circle, I just started at a different point. So, all right, cool. All right, now this one, a little more interesting. So I have my x squared plus y squared again, so bing, yeah. But then I have just a little old y sitting over here. Well, hey, check it out. R sine theta. All right, so let's make those changes out. All right, so right here, that is r squared. And then in place of y, we're going to have r sine theta. Now, technically, we've done the thing, but we would prefer to have it just be a single r. Now, in our Cartesian equations, we normally don't divide by variables. In polar equations, it's a little easier, especially when it's an r you're dividing by. So that is what we would do to quote unquote clean this up. So we're going to divide both sides by r. So we now just have r equals 6 sine theta. So it's just having both sides multiplied by an extra r is just redundant because it would be the same number on both sides. Or if it's 0, we still have an r there, so it would still be 0 equals, but instead of getting a 0 on the other side, now we have actual values there. So later on, we are going to have to reverse the process where we start with an equation like this and we have to go back to the Cartesian equation up there. So just like keep that in mind, like these go both ways, but it can be a little bit of a different thing. Like with the circle up here, r equals 3. Okay, well then r squared equals 9, and then x squared plus y squared equals 9. Okay. You just want to be able to think through both directions on these, so that way you're prepared for whichever way it shows up on the test. And nudge, nudge, wink, wink. Now this one is a little weirder. So this is like a very basic, it's just a line. How bad can it be? It gets weird. Okay. So we have our x and our y. So we're just going to go with our basic x equals y equals substitution. So in place of our y, right, r sine theta. And this equals 3 times our x plus 2. and our x is r cosine theta. Now, technically, it's a polar equation. I'm done. But again, we prefer to get r by itself because if I wanted to like graph this and check that it worked, I don't think I can type just this in Desmos. I think it may not. It might work, but probably won't. Most graphing utilities, you have to get r by itself. All right, so I have two terms with an r. So I'm going to take my 3r cosine theta and subtract it over. So both of these terms on the left have r's, but otherwise they are not like terms. Sine theta and cosine theta, like there isn't some way to mush those together. All right, so I still have the 2, but now over here I have, I'm going to write the r sine theta first, just because the other one has a minus. All right, so they both have an r, so we're going to factor that r out. And then we would just divide to get r by itself. So we will have 2 over the ridiculous sine theta minus 3 cosine theta. So I want you to think about like what this line looks like. So 3x plus 2, I go up 2, and then I count my slope from that. Up 3 over 1, up 3 over 1. Now, imagine putting our circular grid on top of that and like plotting each of those points. So like that starting point, sure, like I got my angle, I got my radius, boom, yes. But to get the other points, like the radius and the angles change in a very weird way when you're looking from a polar perspective. So that's why our polar equation is so weird looking here, because that is a linear XY equation. It doesn't necessarily translate well to polar. Earlier, we had the circle, like the x squared plus y squared equals 9 isn't even a function. But in polar, it's just a number, r equals 3. So depending on the kind of data you have, understanding there are other ways to like use that data coming in and do things with it. That's why we talk about polar here. Because there are some situations where polar is just the better, it makes more sense for the problem. It fits the environment. So now we have this Cartesian one, we're gonna go to polar. So I see the x squared over here, the y squared over there. All right, well, I got my x squared plus y squared, so let's get them together. So I have x squared plus y squared equals 3. All right, now I can make my substitution. Those are the same as r squared. And then just to get r by itself, we have r equals the square root of 3, or r equals the negative square root of 3. All right. So apparently this y squared equals 3 minus x squared will graph a circle of radius square root of 3. So now they want us to take a polar equation, turn it into a rectangular equation, and then use that to graph, like to get a rough sketch. So r equals 2 secant theta. Well, that's just weird, isn't it? All right. Well, I know secant is 1 over cosine. And I know I don't like seeing stuff on the bottom. So like my next gut instinct is clear the fraction. And like I said, it's good to have just those formulas there as a reference. So we're going to multiply by cosine theta on both sides. All right, now when we multiply here, we usually write the stuff that's not inside the trig function in front of it, just so it's very clear that r is not going to multiply to the theta, it multiplies to the cosine of theta. But now r cosine theta, wait, that's familiar. Oh, there it is. So apparently our r equals 2 secant theta is the same as the line x equals 2, which we can graph. And 2. There's all the points that have an x coordinate of 2, vertical line. So this can look more intimidating than it really is, but playing around and moving all the pieces takes some practice and seeing how the pieces like work together. All right, so like 10 can look real intimidating, but remember, we just had that weird fractiony one show up. So maybe this one's another weird fraction one. So let's clear the fraction, see what happens. So we will have r times 1 minus 2 cosine theta equals 3. So I just multiplied both sides by that denominator. This is my result. Now I'm going to distribute. I have r minus 2r cosine theta equals 3. Now r cosine theta, at least, that's x. So I can make that substitution. But r here is a little more problematic. So r, we don't like to do this, but we can do it. If I take my Pythagorean one here and square root both sides, I can have r is the square root of x squared plus y squared. It's not pretty, and we do not want to go through the headache of getting y by itself. That is good enough. So sometimes the conversions are not pretty, but we can still figure it out. All right, now this one, r equals 2 sine theta. Remember earlier I said, hey, we're going to have to do this backwards. Here it is backwards. So earlier I divided both sides of a polar equation by r. Here I'm going to multiply both sides of the polar equation by r. I'm doing the same thing to both sides, but that will make the next step a lot more advantageous. So that will be, there's our equation. So now I have r squared equals 2r sine theta. And now those look a little more familiar. R squared, that is x squared plus y squared. And over here, r sine theta is y. Done. So this is going to be a circle, but because of the 2y here, if we moved that over and did our workaround, we would have it shifted in the y direction. Right. So let me cut it there and then come back for example 11.